happened here, but there's one of them that'll may go away. I don't know. I don't know. So let's just go with this. What we've got. Um, okay. So what I'll do is, I think I can do this. I think I can take a an object, do a copy, go to the next page, and do a paste. Let's see. Yes, I can. So what I'm going to do is I'm going to go in and pick this up. Like last time we sort of discovered, and I wish I could do this, but I can't. We sort of discovered, okay, so we were in here. One of the things that got added is to this picture is I started talking to them about if you had a point on a wheel, and is it coming up on the screen? Yeah. If you had a point on a wheel and the radius wasn't changing, there was no rate of change of the radius, then the velocity would be a painted spot on the end of a wheel that's just turning around and around. And then since that's the case, there would be no change in the radius. That point that's painted would still stay, in this case I said 6 inches away. It would always be 6 inches away from the rotation center. So you'd end up with R theta dot U theta. Look at this. This is the U theta. It's tangent to the rotation path, which is essentially, why you have a U theta and you have a UR. So essentially, this U theta is always tangent. So we end up with this equation for, and here I can do it again real quick so we get an idea of where it came from. Here, I'll do this. So let's just do it again real quick. So we established this relationship from the base vector from last time, didn't we? Remember that? And if you have a vector R that's written like this, then your time rate of change of that vector is nothing more than the velocity. It's nothing more than R dot UR plus R UR dot. If you come over and grab it, you end up with the velocity vector being R dot UR plus R, and I'm getting it from right here, theta dot U theta. So this is an equation that sits in the book. The next thing is that you got to find the acceleration. So with these relationships that we found, it doesn't seem too terribly bad if I look at it like that. Now, the thing is, I've got 5 different things I've got to take care of. In other words, I do R double dot UR plus R dot UR dot, because it's changing. And then I got to do it on these 3. So then I do, and I guess I can do it that way and maybe write smaller. R dot theta dot U theta plus R theta double dot U theta plus R theta dot U theta dot. So it's that chain rule kind of thing, or it's actually product rule, whatever you want to call it, where I'm taking the derivative of here. I don't know why I keep going away from it. Take the derivative of the first term right here, second term right here, and then the third term right here. Here I do the first term right here, second term right there. So I got all this, and it looks terrible, but it's very doable if you pay attention to one thing, and that is this term and this term have to be addressed using these. And if you do that, it turns out to be, you can squish this thing down a little bit. R double dot, well, here, double dot UR plus R dot, and I'll just reach over and grab that. It would be theta dot U theta, if I copied that correct, plus R dot theta dot U theta plus R theta double dot U theta, and I'm running out of room. But if you grab this one, should get minus R theta dot. But from over here, I should get two of them, and then UR. Yeah. It doesn't do good near the end of the screen. Now, if I combine them, I should have R double dot minus R theta dot squared times UR plus, and what you'll notice here, this and this one are the same terms. And because of that, you end up, I don't know whether to put that one first or the other one. I think in the book he puts this one first, plus 2 R dot theta dot U theta. So did I copy all that right? And of course, the truth test is whether or not. Yeah. No, I don't want to always. Here. This thing I can move pretty quick through here. That may be a little too quick. Okay, that's the right section. This is kind of cylindrical coordinates here. Let me try that. This is the kind of the cylindrical coordinates. So the only thing you get extra is this, this, and this. So here, let's see. I think I figured out how to do that. Let's see. Select, trash everything. If I zoom in on it. So if you start with the concept of this, just forget this one and this one, and we're polar coordinates. Then you have R dot UR and that term. Turns out that's exactly what you end up with right here. The question is, did I do this part right? And we may have to bounce back and forth a couple times here. So I get R double dot minus R theta dot, R double dot minus R theta dot squared. Did I do that right? Oh, I'm sorry. He does have a squared. So I think we're okay there. Then over here he has R theta double dot, R theta double dot, and then 2R dot theta dot, 2R dot theta dot. So at least you kind of see where these things come from. Now, all this that I've done may be an entertainment for myself, but that doesn't get you much of anywhere. It's not erasing. Well, okay. That was an R, wasn't it? R theta. So now, how do you solve a problem? That's the next key. And solving a problem, first we got to find one. And what you find out is it's not that awful. Let's see. Just select the whole thing and trash it. So let's run down and try to find a problem first. That's not interesting enough. Let me tell you what, let's just find, here we go. Let's do this one. Slide it over. I didn't do the snippet, did I? New. Should be able to grab all this. I got a little bit of some artifact in there, but it doesn't really matter. for lack of any other place, I might as well just put it right here. Okay. But what you notice up in here, okay, now what he's asked for in this one is just the velocity. Oops. He's just asking for the velocity. He's not asking for the acceleration. If you look up at this term, what you find is you're going to have to determine R. You're going to have to determine, well, for that matter, I'll just do it without the. You're going to have to find R dot, and technically you'll have to find theta and theta dot, and that's it. So if you can find those four, you can find the velocity. So what he's done is he's listed the first one. It's just 0.21 plus cosine of theta. So that's the path this thing is. It takes on that weird looking path right there. So if you go in here and you say, okay, the collar and the collars are pinned at B and are free to move along the rod OA. Oh, okay, OA. The guided curve OC, which is this one, has a shape of a cardioid or whatever. At theta is equal to 30 degrees, the angular velocity is that. So, hey, he just told me that. He also said that this is 30 degrees. Okay, determine the magnitude of the velocity of the collars at that point. Okay, so if you look at it, what I really need to do is the next thing I need to do is I need to figure out R dot. Now, R dot is nothing more, of course, than this, dr dt, which really isn't anything less than that, because the problem is I don't have R as a function of t. And if I don't have R as a function of t, I've got to use this. Now, this occurs in a lot of different cases that you'll find. So you generally have to do something like this. This term is easy because it's nothing more than theta dot, which actually he told you what that was. So eventually you just plug that number in. Now I've got to do this one. And let's see. So 0.2, derivative cosine is minus the sine. So I don't know where to put the minus, maybe right there or here. Minus 0.2. And derivative cosine was sine. No, and the bracket gets closed. And so the next thing is I have this as a function. I'll put the minus in front. Minus 0.2 theta dot sine of theta. Now, he wanted us to find the velocity at that 30 degrees. So what I really need to do is, and here I'll just, for some reason, for my own entertainment, I like to change the, so I don't even know why I should say this, but theta at 30 degrees, this is the dumbest thing I think I've ever said, is 30 degrees. He said theta dot at 30 degrees was 3. But now he wants to know R at 30 degrees. So what you need to do is you need to plug into the equation. 1 plus cosine of 30 degrees. And I didn't start octave yet, did I? Oh, come on. This thing I never quite. Okay, I don't need it to be properties, font. We'll run it on up to there. Oh, okay, maybe that's a little much. Okay, how about there? That's probably doable. Okay, so now I can sort of plug that in. However, I'm going to move it to the, I'm going to move the screen to the right, plug them all in at once. R dot at 30 degrees is equal to minus 0.2, and I'm just filling in for that. So I just write the 3, which doesn't look like a 3. Why did I write a 6? Okay, so write a 3, and then sine of 30. Now I have to be careful, and this comes up all the time, and that is, why do you list this in degrees? And this is never in degrees. Why is that? Yeah, that's okay. So the other question might be, okay, so I'm not sure you answered it correctly, but I'm not sure I asked the question correctly. If you're dealing with everything and your calculator is already in radians, leave it in radians. However, degree means nothing unless it's operated on by a sine or a cosine or a tangent. Then, so that's, you think of it like MATLAB has to have that degree D after it. So that's not normal, but just be careful of that. So if I go with the R, I get this thing closer to me. 0.2 times, and then I've got to do parentheses 1 plus cosine degree of 30 in 2 brackets should get me 37321. 0.37321. The other one, I can, here, minus 0.2 times 3 times the sine, right? Sine degree 30 minus 0.3. That's a 1, by the way, I think. So in essence, what I've done is I've gotten all the characters, all the numbers I need over here. I've got this number, got this number, got that one, which actually I never really need this one specifically. I need this one to identify the location. So you'll never see theta itself in the set of equations. If you look back, I mean, they just don't exist back there. I mean, look back here. You don't see a theta in here. You don't see a theta in here. So there is no real theta in there. But it's implied because somebody's going to always ask you, what is the acceleration when theta is equal to 30 or theta is equal to this or that? So they always ask you that. So this is kind of implied. Now, if you just write the velocity equation down, which is velocity is equal to r dot ur plus r theta dot u theta, then I just fill in. Wait a minute. It sort of jumped on me. So, and this thing is really annoying. So the velocity is nothing more than 0.37321 UR plus R. Whereas, I copied that wrong. Scratch that. I looked at the wrong one. Minus 0.3. Now, 0.37321 times theta. Okay, 3 u theta. So if you wanted to go further, you could say that's that, right? Times 3, 1.1196. So this is the solution you get. Now let's check it, and then I'll come back and ask you something else. Let's check it. It is 1237. Okay, I think, okay. No. Okay, it's 1237. Remember that. Okay. let's see. Well, what he's done, okay, so here's one of his numbers. There's his other. He went ahead and squared it. But let me go back and forth. Okay, minus 0.3. That's what I got right here. And then his is 1.12. 0.12. So that's what I got right there. However, I'm going to throw you something else that he doesn't throw at you that I generally have almost always asked on a quiz in some sort of way. Now, one of the things I don't do is I don't make you work a whole problem like this and then ask that question. Generally, the problem may state here. Let's do it. Let me show you the way the problem might be stated, so at least you see it kind of. So here it is. It's down below us. Okay, switch out, and we'll say the velocity is minus 0.3 UR plus 1.1, here I'll do that, 1.12 U theta. We're at, what do you say, 30 degrees? Tell me what this is in I and J. So generally I either put a box right there or do something so that you're supposed to fill out those two numbers. Any idea how you would progress? So if you think back, you had UR as a function of I and J. For that matter, you had U theta as a function of I and J. Turns out it was, okay, here's the UR. There's your U theta. Turns out it was cosine and sine. And then it turns out it was minus sine and cosine. And this, I can tell you, they will always be this. It's always that. Now, this is the only reason I go through this sometimes is because this might come back to haunt you at some time. If you wrote this out in a matrix form, it would kind of look like this. There comes the Pepsi truck. And boy, he's big. He's a full 18-wheeler. You guys are drinking too much of that. Okay, did I do this right? Is that right? So you could write it like that. You seem stunned. I'm stunned too. I forgot my drink. It's in the car. It's 11:30. I can't go to the car and come back. So, well, he drove off that way. He's gone. I don't know which way he went. I guess he goes over to maybe he goes to the right and goes in behind the lunchroom back there. Delivers back over there, I'm guessing. But I don't see him. Oh, there he is. Yeah, he's going in the back. That's what he's doing. I don't know how he could do it because I don't know how you'd turn around. Of course, if he just gets there and he has one of those drop beds, he can unload and reload. So one way you could do this is just simply multiply this equation in this case, 0.3, multiply that equation by 1.12, and then add them together. But before we do that, well, I guess, let's just do that. Now, if I'm going to do this, I might as well put in the theta, which was 30 degrees. I'm trying to think to myself, what's the most efficient way to do it in this? And I'm not sure I have an answer for that, except, no, there's really nothing I can do except just do it. Well, you know what I could do, though? Here's what I could do. If I want to, I'm trying to figure out a way to make it as painless as possible. So what I'm going to do is, okay, I'm going to create a vector which is called, just call it V, which will have minus 0.3 and 1.12. Okay, so it sits like that, right? And I'm going to do this one. I'm going to write this one with the, not by itself, but with the 30 degrees. So if I do that, and I'll call it T, for capital T for lack of a better name, which actually, the reason I call it T is because it's usually called a transformation. Transforms from one coordinate system to the other. And believe it or not, it almost always works for most. It will work for every coordinate system in existence that has the base vectors of length 1. And there are ones that don't have the base systems, but if you want of length 1, but if you want to get to those are way off in a graduate program. And they will tell you and beat you on the head and tell you they're not base, they're not length 1. So for right now and into the future, base vectors are all length 1. So if I do this, cosine degree of 30, then sine degree of 30, and then minus sine degree of 30, and then cosine degree of 30. If I didn't do a typo, what do you think the inverse of this is? There's something interesting about it. Oops. Take a look, compare these two. Tell me what you think. How are they related to each other? If you look, the diagonal terms remain the same. You just swapped it. It's transposed. This is one of the things, this is an identity. If you've got two base vectors that are length 1 and you're transforming between the two, this always occurs. The transformation is nothing more than the inverse of the transformation is the same thing as the transpose of the transformation. Makes it easy for the math, but it doesn't help us much. What we really want, and this is something I'm going to write out so that we see this a little bit better, because it takes a little bit of getting used to. First step. Wonder if that's going to come in on the video. So really what you want to do is you're wanting to do this cosine theta, sine of theta. You're wanting to multiply this number times 0.3, this number times 0.3 minus 0.3. This one times 1.12, and this one times 1.12. It looks pretty ugly. And then what do you want to do? Since this is associated with the I, and this one's associated with the J, you want to add them up. How would I do that? One, I could, let's see if I can get this to work this way. Now, in your calculator, you probably just want to multiply them out and do it. But since I have MATLAB, this could be one of those MATLAB moments, if you're fine with that. So what you really want to do is you want to multiply something that has, so I'm just going to put down C for cosine, S for sine. Let's see, let's try this. minus 0.3 and 1.12. Is that it? Would that get me that if I did it that multiplication? I contend that that isn't right. I contend that this one is, though. So if I do that way, then I'm basically going in and taking the transpose. Okay, did I do my other vector? Did I call it V? Called it V. Now I've got to do this. V is equal to V transpose. I got to make it vertical like that. And then I got to do T transpose is equal to T transpose. I think T transpose times T transpose. Oh, did I not call it that? No, I called it just V. So it looks like I get, that's interesting. Looks like I get a vector which is minus 0.81, and then the other one is 0.8, well, 82 with that, and then plus 0.82. So it looks to me like that's the case. So I end up with the first one minus 0.82, 0.82. Now I can sort of monkey around and see if this seems right to me. Let me see. If I just sort of draw it, I got a UR that's going backwards. Say that's about 0.3. And let's say this is about 1. So it's got to be 1, maybe about that length. So my resulting vector should look like that. And it's going backwards and up, backwards to the left and up. So I'd accept that to be pretty reasonable. But I may have wasted a little bit of time here, because probably what you would have done is you would have multiplied minus 0.3 times this number and added it to 1.12 times this number and put it right there. And then you would have done minus 0.3 times this number, 1.12 times this number, and put it right there. And that would have been okay. The only reason I do this transformation is if there's somebody who eventually ends up in something like continuum mechanics, that won't be the first time you'll see these transformation vectors. So, yeah. There's some form. Oh, okay. Oh, okay. Yeah. 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 So, yeah, there was probably a couple ways I did it. The simplest way, the one that doesn't require any matrices, is ignore everything from here down and just do that and fill it out, and it'd be okay. Either way, as long as the answer comes out okay. Now, I have almost every time done something like that. Now, this is a lag-on problem, and I don't like to do that. In other words, to get to here, you had to work the problem up there correctly. So what I mean is you're working the problem, and if you mess up and you got the wrong two numbers here, then you'll get the wrong two numbers here. So the way I do it is I'll give a problem up there and the answer's up there. And then I'll just give you another problem. You know, I've done this before many times, and I'll show you what it is. It's kind of funny, but and kind of weird. But hey, what isn't weird? So here. So if I gave you a vector and told you this, 4, 3, 5. Hey, hang on. Yeah, because I don't have time to work another problem. So, and then I said the vector V is equal to, I don't know. How about 3? Ooh, that doesn't look like a 3. Well, I guess it did. 3 UR plus 4 U theta. The velocity now is something I, and something j. What do you think it is? It's a trick question. Some people can see it right off. Some people can't. The people who saw it right off, I went ahead and gave credit for it. And this I probably won't do that same one. But here, let's try something interesting here. Here, lack of a better color. If I draw a vector, okay, there's 1, there's 2, there's about 3. Okay, there's 1, there's say 2, there's about 3, and that's about 4. If you do the math, it turns out it's 5 and 0. If you don't do the math and you just sort of draw it halfway on the page, you look at it and you're like, oh, well, and what's ironic, and since I've got just 5 minutes left, I guess I can maybe do it. If you do it, okay, realize transformation's always cosine, sine, minus sine, cosine. And that's the transformation back up. Ooh, it's jumping around. Wait. Okay. I and J and UR and U theta. Okay. So I'm copying it from right here. Oops. Copying it from right here. If I copied it from right there, you look at this for a minute, you'll say, hey, wait a minute, cosine of whatever that angle is 4 over 5, right? Does that make sense? And the sine is 3 over 5. Okay, so if I want to, I can go in, say 4/5, 3/5, minus 3/5, 4/5. Now, if you want to, whoa, hang on just a second here. Go down. Okay. Man, you got to be careful. So if you want to, you can take this and here, 4/5, 3/5, 3/5, 4/5, and then 3 and 4. Now, got to be careful. What do you think those would be? Okay, so if you look at the first one, okay, we don't necessarily have to do the math, but if you do this, 3 times 4, so what you get, 3 times 4 over 5 minus 4 times 3 over 5. Oh, that's easy. But 3 times 3 over 5 plus 4 times 4 over 5, what's that equal to? So if you look at that vector, the top number should be 0. Bottom number should be 9 plus 16 over 5, which should give you 25 over 5, which should give you 5. But, you know, for people who just looked at the drawing and figured it out, that's okay. So I always give a problem like this. I always give this thing with, I don't give it that way. I give it this way. I give it this way, just in case you forget it. For that matter, you can do it this way. I, J, and then the transpose of that thing. Oops. Cosine theta minus sine theta, cosine theta. And then this really looks ugly. UR and U theta. That's just taking the inverse or the transpose of this thing, moving it to the left side. So again, the only reason I do this is to get you ready for this concept in case, and it's not too damaging, I don't think, to your mind, is it? I mean, did it make kind of sense? Something that he doesn't generally ask, which doesn't mean that it's bad, I guess. I don't know. Okay, what do I do? Okay, what did I do? Did I do that? And then I did everything. Okay. So I really don't necessarily have time to. I was on page 67. That's close. Well, yeah, maybe not really close. But I hope when I bring up the document again, I go right back where I was, but I doubt it. So what we'll do is we'll come back and work this for accelerations as well. What you find out is even though the derivation of the equation is nasty and evil, really the implementation is not that hard. Actually, I think I'm almost sure I did this problem on the assignment. So, oops, that didn't work. Okay. Okay. So I guess go find a Pepsi.